Okay, that looks good. Camera. Awesome. All right, so for today's class, we're going to pretty much wrap up the applications of exponentials, right? So the past couple of classes, for class 1 anyway, have been going through the exponentials and logarithms type stuff. We're going to wrap it all up with applications for exponentials. Probably, maybe the hardest of the application style questions, this particular area of study. I'm not sure particularly why. I suppose the sorts of things you have to consider, there's a fair bit that you have to consider when creating your equations and actually working with them in the context of exponential growth. Maybe it's just not super intuitive and it takes a bit of time to get used to. And so basically to help with that, we're going to have a look at essentially how you can treat each type of term of the exponential as its own dedicated use case, right? You can use different key information from the question to solve what that term will have the value of. So the first thing we look at is this idea of the initial value. So the coefficient at the front of your bare bones exponential is typically referred to as the initial value of the equation. And the reason why is because when we think about initial value in pretty much any of the application style questions, that's where the scenario is at time t equals 0, right? After no time has elapsed, the exact starting point of your application style question. And so, we have a generic exponential equation of t, and so if you were to sub in t equals 0, you would see that the exponential term itself will decay off. It'll disappear down to just 1. So when you're subbing in t equals 0, you are left with that leading coefficient. And so for that reason, if you ever know the starting value of your scenario, and you know that it's an exponential type scenario, you now know the coefficient, or rather the leading coefficient of your exponential term. Now, a lot rarer will be the case where you have an exponential that has a vertical translation attached to it as well. I haven't actually seen it come up in a scenario, but I figured it was worth pointing out because technically, yes, exponentials can have these vertical translations, and so for that reason, it's worth pointing out that if you sub in t equals 0 into those kinds of exponentials, your initial value will be split across both n0 and c. This is more just a warning. It's very unlikely for you to come across this. So that's initial value, right? If you ever know the starting position of your system, it'll basically be the leading coefficient. Next up, how do we handle the base of the exponential? So if we think about how exponentials work just in general, when you have a larger base, the exponential will rise faster, right? If you compare 2 to the x to 3 to the x, you can see that for the same values of x, g of x is going to rise significantly faster. In the context of your application style questions, you're typically choosing your base to match the growth rate in the question. Now, worth pointing out, you might not always be given the growth rate, but where you are given the growth rate, you'll be able to immediately substitute that in to your exponential. A very typical example of this is going to be something like cell growth. You'll have a batch of cells on a petri dish or whatever, and it will double every fixed period, like let's say doubles every 15 minutes. The fact that it doubles means you're going to choose the base of your exponential to be 2, because every time your power rolls over to the next integer, you are in fact doubling that exponential. If it tripled, you would then choose a base of 3. One of the last things that comes up is the exponential coefficient, k. So you'll have some sort of coefficient attached to your t value. This one's less likely for you to be able to just sort of look at a value and immediately sub it directly into your equation. But there are certain circumstances where you can achieve that. It's typically, when you can just slide it directly in, it's under the circumstances where you know what the fixed period of growth actually is. Like I kind of mentioned earlier, like this idea of doubling every 15 minutes. The fact that it doubles means you choose your base of 2, but the fact that it's every 15 minutes means you're going to set your coefficient on the t variable to be 1 divided by 15 minutes, or 1 divided by 15 rather. And the reason why you do that is because an exponential with a base of 2 will only double its previous value every time you hit the next integer. So from 1 to 2 to 3. So if you divide your t by 15, what you're essentially doing is delaying how long it takes for you to hit that next rollover. And so, 15 over 15, that's going to roll over to 1. You've now doubled. 30 over 15 simplifies down to 2. You've now hit the second integer, you've now doubled again. So if you know what the growth rate is, if it is some if it is some other value than 1, then it's a very easy way for you to just sort of plug that one in. Although I will say, most fixed periods are going to be 1. Something like growth rate every 1 month, growth rate every 1 year, right? And so in both of those circumstances, the coefficient is going to still be 1. The only thing that changes is what your time value will be written in terms of. It'll be written in terms of months or years or whatever the time value specifically is for that one. So that's when we have everything given to us on a silver platter. Sometimes we don't quite have all that information up front. And so just a few tips. If there's no growth rate specified, right, if there's nothing we can just slide into the base spot, you just choose whatever you darn well please. You can pick literally anything. What will change based on your decision will be your result for the k value. Right? So there's a bit of a push-pull between the base and the k. If you choose a different base, you'll get a different k, but both of those will essentially work together to still make your exponential work out well. This book in particular, so the Cambridge Unit 1 and 2 book, will refer to this idea of a generation time. This is defined as the time it takes for a batch of cells to double. This is pretty much entirely isolated to the Cambridge book. It might be in the Jacaranda book, I didn't actually check. This isn't like a VCAR standard thing they're expecting you to know for methods. This is just what they mean when they refer to generation time. Reason why that's important is because it contains 2 sets of information. The time it takes, so that's going to be your coefficient k information, and the fact that it's doubling. That's your base, being 2. So knowing this one phrase will get you 2 pieces of information out of it. Another thing that comes up fairly often is this idea of a decaying exponential. This is when you have a negative in the power of your exponential because, well, the values decay over time. When you have either negative x, as x gets larger, your y values get smaller. They decay closer and closer to your asymptote. So there's a couple of ways you could do that. The first is to make your coefficient k a negative number. Obviously, that's your e to the negative x example. The second, which is a little bit less common, is to actually choose your base between 0 and 1. We explored in one of the lessons that when your exponential has a base between 0 and 1, it's effectively the same as a reflection about the y-axis. You get this sort of flip effect occur. And lastly is the definition of half-life. So the book will use half-life. This just means the time it takes for a radioactive material to decay to half of its initial value. So if it starts at 10 grams, the half-life will be however long it takes for it to finally decay to 5 grams. That's pretty much it there. This is very application heavy, so what you do will depend on the information provided to you. And so I think one of the things that would be a good idea for this one in particular would not necessarily be to do breakout rooms for this one, but to sort of field potential ways of solving the question from everyone. I might go through a few myself or at least mostly guided by myself, just so we can all be on the same page as to the kind of thing you would do to solve these kinds of questions. And then we'll eventually field even more participation, getting you guys to eventually drive the whole thing, if we can get there. Because as I said, this is a bit of a difficult one. Learning the applications of exponentials is on the harder side. In fact, that's why I created this document around it and also contained all the work solutions document, because I know it's one of those that takes a fair bit of playing around with. And so what I'll do is Yeah, why not actually? I'll drop this entire thing in the chat so you can play along with that. Um, Technically, that does mean you can cheat when you're giving your answers, but if you are cheating, it'll be fairly obvious when I ask a follow-up question. So at least that way you'll have something to follow along with as we're going through it. That's in the chat. Sweet. All right. Was there any questions about the overall framework and like assigning particular roles to variables? I'm happy to explain any or clarify anything before we dive into questions. All right, nothing. Easy. Let's make a start. Cool. So, population of 1,000 E. coli bacteria is going to double every 15 minutes. Determine the formula for the number of bacteria at time t minutes. I think, yeah, at the top of this, yeah, it does. So if you just sort of go through, have a read of the top of this, it reminds you of essentially what the what each term is going to be controlled by as far as the key information you're given. We have a starting value of E. coli. We're told that it doubles, and we're told that doubling takes 15 minutes. What kinds of things can we start to do to put this exponential equation together?
We can establish the base as 2 because it's doubling.
Yep, establishing the basis too sounds like a pretty good idea. For those who are new to this, by the way, I have a couple of screens. So when we go through this, through the work solutions together, there will be another camera that is just pointed at my phone. We do handwritten notes on that, so be sure to look out for that one. But yep, okay, so base is going to be 2 for that. That's good. What else could we glean from our information? Okay, what about this population of 1,000 E. coli? What could that relate to when it comes to creating our equation? That's going to slide in somewhere. Is that the initial A? It sure is. Yeah, that's the initial value, and so that's going to be the leading coefficient there. So initial value, that's our initial starting population of E. coli, and so we're going to put 1,000 at the front, which I obviously didn't leave myself too much space for. 1,000 bracket 2. Awesome. All right, that's good. We talked about how it doubles. We didn't mention how it doubles every 15 minutes. So the fact that it doubles every 15 minutes is another key thing for it. What can we now do to finish up this exponential?
In the power, could we put 15 plus t over 15?
Power is
The
15 plus t over 15.
Yeah, because 15 on 15 would just be 1, right? So that wouldn't be doubling.
15 plus t on 15.
No, like
Um,
15 plus t all over 15.
oh, all over 15. Yeah, okay. I see why you've done that. I'll show you with a couple of substitutions what's happened. If you sub in t equals 0, what do you get as a final value? You might be able to see it.
Oh yeah, never mind. That's already doubling.
No, it's still, yeah, you're doubling, which
It's
is,
gonna be 2000 then.
repeat that, sorry.
If you put t is equal to 0, it should be like you're gonna get y is equal to 2000.
Yeah, which is too much. We want t equals 0 to equal 1,000, which is why we're not going to have this 15 plus. And so, yeah, to help you out, Michael, it's not going to be 15t, it's going to be t over 15 because you want to divide how long it takes for you to get to that value. If you did 15 times t, you would be doubling 15 times faster than you would want to. Because yeah, again, you can test some values. If you sub in t equals 0 into this, you're going to have power 0, so that's going to cancel out y is 1,000. But when you sub in 15, now you're going to get that that 2000 value that we would expect to happen. And that's it. That's the whole thing. Cool. That's formula. These are all CAS, by the way, so we won't be doing everything by hand. Next question is a fairly stock standard one. This has got basically nothing to do with exponentials. You solve this the exact same way you solve every other function type thing. How long will it take for population to reach 10,000? The only thing you need to know there is like, what equation did we just create? How do we interpret what we just made?
We put 10,000 in the y and then we solve for t.
Yeah, 10,000 in the y, solve for t. And then Michael's 15 log base 2, 10. Yeah, probably after all the rearranging there. So yeah, you can absolutely do. Yeah, correct. He's got it. Nice. Yeah, you can absolutely rearrange that yourself. This one being a CAS, obviously you save yourself a bit of the hassle, but it doesn't even take that long to do the rearranging. Yeah, so we're looking for 10,000 is equal to our function, just so we can have it on the screen. Whoops. Equals 1000 times bracket 2 to the power of x over 15, comma x. That's going to get... Now the CAS, I guess it's worth pointing out how the CAS does things. It defaults to natural log for whatever reason. It doesn't seem to like using any other log base. So when you get a nasty looking thing like that, just keep in mind it's only because the CAS is using natural log. If we do compare the equivalent log base 2 one, so if we do 15 log 2, what was supposed to be 15 log 2 10. If we then compare that, you'll see we get the exact same result. So just different ways of expressing the same logarithm. Cool. All right, that's one down. Next up, half-life of plutonium, 24,000 years, 10 grams present now. How long will it take until only 10% of the original sample remains? A similar kind of question. So I think I'll leave it up to someone to start us off. It's one where it's a little bit less clear what immediate information we have, or at least it's clear the immediate information, but not how that necessarily translates to an exponential. As I said, you won't always be given everything off the bat. Initial value 10, yeah, perfect. 10 grams are present now, right? Initial value 10, which means that our leading coefficient is going to be 10. Nice. Is it that whole thing? 10 by a half. What do we got there? 10 times half power t over 24,000. Half times a half. Did you mean to have a base of half or base of 2? I don't think I'm half a half-life. No, so not half a half-life there. The way half-life just tells you the time it takes for a radioactive material to decay to half of its initial value. So half-life is actually a point that's known on the function. It's the time t equals 24,000. Yeah, time t equals 24,000 and mass equals 5. Half-life actually is an information about the point on the graph. So you're very actually close to getting the full thing off the bat. Getting the divided by 24,000 seems like a bit of a fluke now that we've had a discussion about that, but it was pretty damn close. Like literally, if you just wrote base of 2, you would have got it just sort of by happenstance. The key thing here is to realize that we don't actually have base information, right? There's nothing that tells us about the growth rate necessarily. Kind of does, but you'd have to spend a lot of time trying to figure out what this actually means as far as growth rate. So this is a scenario where you can just choose whatever base you like. Now choosing a different base will mean that your k value looks different, I pretty much default to base of 2 because it kind of does what Michael saw, which is when you have base of 2, as it turns out, this 24,000 ends up usually just being 1 over itself, 1 over 24,000, and we'll see what that looks like. So we have 10 times base of 2, we have some unknown k, and we have t. As I said before, half-life is a known point on the graph. So we know we started at 10, which means we'll end at 5. 5 times 10, 2 to the power of k, and then t was our 24,000. T was our 24,000, k is the only unknown in here. So we do use some sort of, it's not quite simultaneous equations, but it's this idea of sub in a bunch of values and then you can solve the remaining unknown with it.
Chris,
Yeah, what's up?
so we can just choose the base when it's not specified.
Correct. Yep.
Okay, so that wouldn't it like actually affect our actual like our answer?
It will. What it'll do is if you choose anything other than 2, you won't have 1 over 24,000 as your thing. I'll do 2 ways of doing it. I'll do a base of 2 right now and then get you the answer for this one. Then we'll do whatever base you want, and then we'll show you that you still end up with the same thing.
Yeah.
But okay, yep, you sub in that. Sub in y to find any k. Yes, that's correct, Michael. You sub in your point, and because you've only got k left as the only unknown left, you'll get that k value. Now, that'll be just a CAS solve. All right, I've kind of already got these pre-written anyway, so we might as well just go straight for it. K equals -1 on 24,000. This will just be a CAS solve, though. So when we write out our final equation or have it defined in the CAS, we've got 10 bracket 2 negative t over 24,000, and that gives us everything we need to have our full equation. We can now answer anything we want about it, which in this case, it's asking us how long it'll take until only 10% of the original sample remains. So now that we have the equation, what could we potentially do with it to answer that question? Sub in y equals 1 to find t? Yes, y equals 1 is correct. I'm assuming your logic there was if we're starting at 10, then 10% of 10 is going to be 1. So the fact that it's 10% of the original sample means that you are left with 1 gram left. And yeah, obviously when you replace your y with 1, you've only got t left over to solve. So you'll just CAS through this. 1 equals 10 bracket 2 power negative t over 24,000. This will be CAS, and I'll just sort of cheat out the answer from the pre-written answers, which is going to end up giving you t equals 7, 9, comma, 726. Now, it is application style. Make sure you give units for these things. Because your t information was in years, 24,000 years, and we didn't change any of that before putting it in the equation, it means that everything that we have in our equation is going to remain as years. So that's going to give that. Now before I move on and answer the other question, is there any questions about how this has worked right now? Because after this, we'll choose a different base and see how you still get the same answer. Y negative t and positive t, because it's decay. Yes, technically, that is the answer. It is a decaying thing, but we're not choosing negative t. That's just what the CAS solve would give you. Like if I just go through and CAS solve out what you would have had, we'll have 3, 1. We were going to do 5 equals 10 times 2 power of k. Let's just do x. X times 24, 1, 2, 3. If you solve this for x, it will just come out negative. So yes, it's negative because it's decaying, but it's also negative just because that's what the math would force k to be. Sweet. Yeah, okay, that's that one. Next up, so what happens if we chose a different base? So let's just choose even something ridiculous. Just smack the keyboard a couple of times. Stupid base, right there. Okay, what do we do from here? Well, the stuff that we did know was we knew the point, the half-life. So we knew that at 5 grams, it takes 24,000 to get there. So times 24,000 for years, and this x is going to be, you know what, I'm just going to put k there, just so we're not confused. What's going to change quite rapidly, mind you, will be what the actual k value is. So instead of having -1 over 24,000, we now have a completely different k, which is, well, quite frankly absurd, but you know. Now, from there, we will put this back in as our new k value. So instead of having the -1 over 24,000, we now have this monster as our k. We have t as the unknown, which I'm just going to use as x. We have 1 as the final value. I'm just going to go all the way to the end to then remove that k. And if I control enter, we're still going to get 79,726. Obviously there's some decimals, but I rounded my answer the first time. So choosing whatever base you want will mean you get a different k value, and those two together will compensate to create an exponential that will still work out to do what you want it to do. You know, don't go out of your way to just choose a different base just for the hell of it. If you do get an immediate, obvious base to work with, then just, you know, don't put too much more effort into it. Just you've got it. But you know, this is just to demonstrate some stupid base, stupid k value, but you still end up getting there fine. So as long as you're following these steps to achieve your, as long as you're something in a known point, the rest of the exponential will work itself out. Any final questions on how that one's all worked?
Chris, would this type of question ever ask for the equation?
Can you repeat the question, sorry?
So like, would this, you know how this question is just like asking for when there's 10% left?
Yep.
Would this like, given like, you know how there was not much given, like the base wasn't given and stuff?
Mm-hmm.
Would this type of question ever ask for the equation?
That's a really good point. Because if it asks for the equation, obviously you'd have to give a valid equation.
Yeah.
If they do, and your teacher hasn't considered this, then the question is written poorly. You'll still be fine though, because there's a couple of things you can do. One is just obviously, you know, choose your default base of 2 and then work from there. The other is when you define something in the CAS, so when you define one of these exponentials, like let's say we grab this one, this nasty one. I don't know exactly what this is going to look like, but we'll see what happens. The CAS will do something to make it look, or basically it'll simplify the base and k value into just a single term. So if I define this as h of x, I don't really know what this is going to look like. Let me just make sure I got everything. Coefficient, base, k, time, that should work. If I now reprint h of x, it'll do some magic to simplify everything down. And so that's another way you can get around it. If you have chosen a strange base, then one of the things you can do is just define it in the CAS and let the CAS do some simplifying stuff. Michael, they probably assign a base in the stem of the question. Yeah. So if they are caring about the equation, like in 1A, they cared about the equation, the base would have been obvious, doubling, right? Well, sorry, the base is implied to you. It may or may not be obvious. So yeah, if they care about the equation, they should force that. If they haven't, and the question's written poorly in your SAC, because to be perfectly honest, some teachers don't necessarily consider absolutely everything if they're writing the SAC from the beginning. This is a nice little fallback you can use. Just whatever the CAS gives after simplification is probably your best bet at hedging your bets there. Is that all fair enough?
Yep.
Easy. Cool. All right, that's that. Question 3 is a very similar thing, although there is one difference in it that you're going to be following the same steps overall. I'm curious to see how we go.
Is this question 3?
Yeah, question 3, carbon 14. What could we do to start this off? We'll have half-life, so we know how to use that. We're getting less and less information over time. You can take a peek at the answers as well to sort of inform your next step. But obviously, give it a solid go yourself if you can.
We only have t given as there's no base, no initial value, and no k.
Yeah, solid. So we have our time value. Now, I will say half-life isn't just a time value. It gives you something else that comes along with it, and that becomes important. What else does half-life give? What did it give in the previous question?
They give us the years.
Yeah, it gave years, so that's time. It gives another thing as well as part of it. Maybe
The value on the other side of the equation.
Yes, correct. It's usually referred to as final value. What's left after the half-life? Yeah, so it's actually a known point. You got your XY pair or your NT pair, I guess. Yeah, so the fact that it's half-life means whatever we started with. Now it's unknown what exactly we started with, but we do know that after 5,730 years, we're left with half of that value, whatever that value is. That's going to be an important distinction to make when it comes to solving stuff for this equation. There is at least one thing we can default slide in here.
Is it the base?
Yeah, the base. We can choose pretty much whatever we want for this. Usually I just default to 2, but again, we've demonstrated you can pick whatever. Someone shoot me a base. What do we want to use? 17? Sure, why not? Base is 17. And the rest of it's unknown. There's no other stuff. So we have n0, we have k, we have t. There's no immediate stuff that I'm seeing here. And, you know, again, there is kind of a little hack for half-life stuff. If you do choose a base of 2, we saw before, base of 2 meant the k was -1 over 24,000. That actually works out to be the same thing for 3 as well. If you choose a base of 2, you can get your k as -1 over 5,730. But, you know, that's only going to really work with half-life questions. So, nice hack, but only works with really one kind of question. So it's good that we're generalizing it. This is actually everything we can grab out of the information right now. What can we do to start solving for some of these? Can't we assign 50 and 100 for A and A0 respectively? Yeah. That will work. That will work. I'm just trying to figure out if the teacher would start raising a fuss about that. To make it super general, the way you could do that a bit more mathematically sound would be to say half n0 on this side and n0 on this side. And the reason why is because now you're treating it as a variable rather than just shoving in a value. Now, it will still work. You just got to pick something and then half of that thing. It's still the same thing, obviously. But this will probably turn less eyebrows at your working out. Because now when you do this, you'll notice, I got n0 on both sides. Oh shit, look at that. I've only got, oh sorry, I didn't put the t value in. Right, that was the whole point of half-life. Because this half of the final, or half of the initial value, only came about from 5730. So now you've got half equals 17 to the power of k times 5730. Actually, I do have to carry this one out because we've got a base of 17. So let's cancel it out. 93.1, 0.5 is equal to 17 power of 5730 times x, comma x. That's going to give us that. And so our function is therefore going to be, going to stay n at the front. Maybe I can say n0. Might be able to do that. Times 17 power of x times that. That's our k value, reminder. I just used x as a stand-in. And yeah, that's everything we know about our function. Cool. All right. So we got our k value, which is good. What can we start doing now to solve the final question, which is we want to figure out how old the fragment of cloth is if we now know that it has 40% of the carbon-14 that it initially had.
We can use 0.4 as our final value.
Yeah, that's like 99% of the way there. There's one kind of thing we have to do attached to it a little bit. So 0.4 equals h of x, comma x. There's one thing we've got to add to this 0.4 to make it not just a number, but related to the scenario. Because if I just do this right now, we run into a bit of a trouble because we've got x and n naught in the equation. .4 being 40% is absolutely good. 40% of what? We do the assume line and then n naught equals 1. Assume naught. Not too sure I catch that. We do the assume line and then n naught equals 1. Are you as in what to say? Provided n naught equals 1 and then cancel it out that way. I mean that's kind of like what you did with the 100 and the 50, which yeah works. But the other thing you just do is you could just tack on n naught here, n naught, and that'll disappear. But yeah, so what you're doing is fine, right? Writing them as percentages or writing them as decimals as whole numbers, that's all totally fine. But this will be at least a little bit less sus when you're writing out your answer. And then yeah, if we just control into that, for those who are following with the answers, that'll be the right time value. 7574 in years. Well, hang on, was it years? Let me double check. Yeah, years. 7574 and so 7575, obviously rounding up there. Yeah, that's my bad. So yeah, overall the same sort of thing. I guess what we're seeing now is we don't necessarily need to have every piece of information to solve a thing. You just need to solve as much as you can out of it. In the very beginning, we had literally everything given to us as key information. In question 2, we had to decipher what half-life meant for an equation. And in question 3, we had to... and we didn't have base. That was the other thing. And in number 3, we also didn't have the starting value. So there are other ways, of course, of getting things as we've just described. Question 4 is a lot more chill. Question 4 is basically what you would see in every other kind of question for any other area of study. Both of these should be fairly chill. So have a read of question 4. Let me know how we're going to go about that. So again, this is one of those where you just sort of got to know what actually is my equation. It's P of H. What does that even mean? It's like how when you do quadratics, you have like a of x, which is your area with respect to length or area with respect to width. You got to figure out what each of the variables are tracking, and then that informs how you grab whatever's in 4a or 4b. This one is a bit of a struggle then, maybe. Find pressure at height of 5 kilometers. Okay. So pressure is what we want. Height is what we're given. So that's our key information there. Height, we now got to look and figure out where is height in our equation. There we go. Height is the h variable. Height in kilometers is h. So this height of 5 means that we can replace this h with 5. Find pressure. Okay, where's pressure? Okay, here we go. Pressure is P. So pressure is whatever's left over on the left-hand side. So finding pressure at height 5 kilometer means you replace your h with 5, and then whatever's left over is your pressure. Specifically,
which question is this?
question 4.
Oh, I can't really see it on the actual. Oh no, actually you can.
You can?
I
Okay.
just zoomed in a lot.
Oh, sure. Yeah, okay.
Yeah.
Fair enough, fair enough. All good. Yeah, in fact, that's probably another thing worth pointing out. Like, I think I've sent, maybe I'll have to do it again. The textbooks. The textbooks are all, oh shit, I didn't give the, yeah, that's why you don't have it. Because, the classwork doc, because we didn't do breakout rooms, I didn't think. Yeah, okay. Let me just grab that real quick. What we typically do is we chuck these Word docs in the chat. It contains a link to grab all textbooks, whether it's Jacaranda, Cambridge, or whatever, Unit 1, 2, Unit 3, 4, and it pretty much details what we've just discussed, where you can follow up with the key questions and practice for those. I essentially go top to bottom on all the relevant stuff and say, hey, look, these questions are this kind of question. These questions are this kind of question. So for instance, you might have seen that like question 1 is its own thing because you have everything. Question 2 is its own thing because you don't have the base. Question 3 is kind of like question 2 because you also don't have the base, but technically you also don't have the initial value. I kind of grouped them into similarity, and then, yeah, it's a thing that you can follow there. And the reason why I bring that up is because it means you can also have your own copy of the thing without relying on whatever screen share nonsense that I've got going on. But okay, cool. So question 4, as I described, we're just going to sub in basically h equals 5, which obviously makes it a bit weird when I've defined my function as h of x. It says give it to nearest millibar, so all you have to do is ensure that your equation is in the appropriate unit. It does say pressure in millibars is what P of H is, so there's no conversions to be done there. If you did need to convert, for instance, from millibars to bars, it's the same thing as converting from millimeters to meters. So you'll have your SI units. Remembering how your conversions work between SI units, or at least they're not called SI units. They're called because SI unit is like your meter or your bar. I forget what the suffixes are called or the prefixes are called. Anyway, it's based on SI. I'm sure you ought to look it up somewhere. Oh yeah, and then part B, right? Height and then pressure. So I'll let someone take that one over. 4B. What's the only nuance we have to do there?
Solve T for 400.
Yeah, exactly. Solve T for 400. So that's just going to be a CAS solve, nice and easy. You're told pressure, so you give pressure as 400 equals function, comma, x, just because I've defined mine as x, to the nearest meter. Now, this one's nearest meter. Remember, our height is in terms of kilometers as far as the equation goes. So we've got 7.33 kilometers. Let's convert that to meters. Right. Let's do that slightly better. There we go. All right, easy. Question 5. Biological culture contains 500,000 bacteria at a particular time on Sunday. Culture increases by 10% every hour. So this will be a fun one to play with for a bit. Increases by 10% every hour. What time will the culture exceed 4 million bacteria? Have a think. Let me know how you might start it out.
N naught is 500,000.
N naught is 500,000. Yep. That's our initial value. 500,000.
Because it's increasing by 10%, we can have a base of 1.1.
Yes, that's really good to point out. 1.1, increasing by 10% every hour. Yeah, this is where you just have to be remembering how decimals work as far as like percentage growth rate. So doubling is 2 because you're sorry, I'll answer that in a second. Doubling is 2, but when you have something that's not a double, when it's like some sort of percentage in between 0 and 100%, you're tacking that onto your leading digit of 1. All right, some people will accidentally go ahead and put 0.1 in there as a base. Don't do that. And then for Michael, if we did a base of 2, would this be wrong? Well, let's find out. Could we do a base of 2 for this one? Yeah, you could. We'll see how that one works after we finish this way of doing it. I reckon you could still do a base of 2 with this. You'll just have to play with it a little bit more. But yeah, definitely we'll have a look at that. But okay, so base of 1.1, 10% every hour. It's not, yeah, it's 10% with respect to the initial 100%. So you start with your 100%, which is base 1, and you're tacking on another 0.1 to make it 10% more. Anyway, I just know some people get that back to front a bit. That's that key information there. That might be it. Yeah, because it's, well, this is kind of part of it. Every hour, actually, this is part of it. Every hour tells us what as the final thing for this exponential equation.
We can like assign a variable, like any variable at x as like hours, and just slap that on 1.1 as an exponent.
Yeah. So basically, just are you saying like leave it as just the variable?
Yeah, just like that.
Yeah, correct. Because yeah, we're increasing by every hour or every 1 hour, so it's 1 divided by 1, which of course just disappears. There's no more coefficient there. Nice. That's our full exponential. At what time will the culture exceed 4 million bacteria? I mean, at this point, we've kind of already answered this kind of question before, but why not? Let's just drive it home. What do we do once we have this?
Solve for 4 million.
Yeah, 4 million. So you just put your 4 million on that side. You bring all of this down. You've only got t left. It's a CAS solve. Now, to answer the other interesting question, what happens if you choose base of 2? A bit of math, I guess. So you would start with your 500,000. You have your base of 2. You now have a k up here because you can't rely on the fact that it's 10% every hour, because otherwise you'd have a different base for that. Now, the fact that it increases by 10% every hour means you sort of have to just manufacture what your next point is going to be. Because if you sub in a point into this, so a t and a y value, you can then solve for k. There's a way to manufacture a point for this. It does have to do with the fact that it increases by 10% every hour. How could we create a point to plug into this equation? And by point, I may need a time value and a corresponding y value. increases by 10% every hour. The 1/10 with t equals 1. The 1/10 with t equals 1. So when you sub in t equals 1, you would have 1/10 left. Is that what you're saying? As in 1.1? No. Oh, 1.1 n naught equals n naught. Yes. Yeah, that's it. Yeah, correct. Because it's 1.1 of our initial value, which is 500,000. We know that one. So if we just figure out what 1.1 of 500,000 is, so let's knock this over. 500,000 times 1.1. This will be the next value that we would have. So when we go through and do cas solve, here's our final value. Here's our initial value times 2 to the power of k times t, which is 1, because that's after 1 hour. Is it hour? Yeah, 1 hour. Solve for k, you're going to get a sort of k value there. Now when we go ahead and plug that back in, we're going to have our k, this is going to be our t. Grab that. And then still want to keep that, but now we're solving for 4 million over this side. So 4, that's probably enough. How many is that? 1, 2, 3, 4, 5, 6, too many. No. Yeah. If it's slightly off, I'll fix it. Solve for x, 21.81, and then, in fact, let me just check the answer to make sure that was right. 21.8, yeah. So that's the same t value. If you're following along with the answer sheet as well. The answer sheet that I provided had a base of 1.1, also got 21.82. Now 21.82 isn't the final answer though. If you want to make this really nice and special, it does say at what time. And while t value and while your value of t does correspond to a time, there's a way you can make it a bit nicer because we are told a bit more information that we can work with. What can we do with this? 21.82 hours. Yep, cool. So definitely putting on the fact that it's hours. Now, if I asked you what time it was, and you tell me 21.82 hours, I'm not going to really know what that is. I've got to have an idea, because if I think about 24-hour time, this is where double checking the key information you have, right?
Is the answer going to be 10 a.m. on Monday?
Close-ish, yeah. For 9:49 on Monday.
No, but isn't there like a assumption like if it increases by 10% every hour, don't we like assume that it's only going to increase as it strikes the hour, or like because that's what like we usually do in school, but I'm not sure if that's how it works with here. If you or like if we're assuming that it's like gradually increasing.
Yeah, so what you're touching on there is the fact that our model is only accurate on those breakpoints. Now, obviously, in the real world, biological things don't just sort of step change in terms of their population. At what time will the culture exceed 4 million bacteria? Yeah, they could have tightened up the language around here to say at
To the closest hour or something.
yeah, to the
Because like
closest
I know
hour.
like when we do like finance and stuff, right? Like
Hmm.
when we do like loans and like they say like in how many years will like some like such and such like reach a certain value like an investment, and
Yeah.
you have
Well,
to always do it like to the year, which I'm guessing because it's per annum, right? But
yeah, because it's paid out on a yearly basis, whereas with biological cultures, they don't step change their population. Now, if you wanted to attack the fact that our model will only be accurate, like we're technically interpolating, we're assuming what's happening in the middle of between our 10% increases every hour. Like again, I guess what we're saying is we're assuming this is exponential growth that's modeled perfectly by this. Whereas, I mean, maybe it's perfect, or maybe it does have a bit of error in between the integers. Um, to give the short answer, the book doesn't think about that. The book just actually gives a decimal. Didn't even bother converting it to a time. So I guess ask your teacher as far as SAC is concerned. As far as exam is concerned, pretty sure you want to give your time to the nearest minute in most cases. And it'll tell you in the exam. It has to be bulletproof on the real thing.
Yeah, okay, yeah.
And if it's
Cool.
not bulletproof, then by God, help us all.
Yeah.
But yeah, that's a good question. Good question. But yeah, converting to for those who might be still lost as to how we even got that time to begin with, this is 21.82 hours after 12 p.m. So you just start at 12 p.m. You're like, okay, add on my 21.82 hours, and then just convert up for the for the minutes.
Chris, I just looked at the textbook solutions and even though like it says, 21.817 and whatnot,
Yeah.
the solution like says like 22 hours, like as like I said.
Oh, it did round it up anyway.
Yeah.
Yeah, okay.
So I'm guessing it's sort of like going with like how I was telling you about like the finance and
Yeah,
stuff.
yeah.
It's
No, I get you.
going off an assumption.
Yeah, I mean it's perfectly fair to consider that. The real answer is they should have tightened it up in the book a little bit more. But yeah, I could go either way on that. Just sort of thinking about like the underlying biology. I would expect you probably wouldn't round that way, but that's what they've done. Just to answer the other question. Don't know if we still have time, but how do we convert? Oh, how do we do that conversion? Yeah, okay, that's fine. In fact, I can just show it. Where is it? Is it even shown? Yeah, okay, here it is in detail. Cool. So 21.82 hours is the answer that we arrived at. Now, a reminder that our starting value was 12 p.m. So 12 p.m. on a Sunday, plus an additional 21.82 hours. You start by adding. In fact, what did I do? I started by splitting up your hours into hours and minutes. So 21 is obviously going to be your 21 hours. And then 0.82 hours doesn't actually just mean 82 minutes, as a lot of people will accidentally do. It's 0.82 of an hour. So, in other words, 0.82 of 60 minutes. And so, in total, if you add 21 hours to this, you're going to hit 9 a.m. on Monday. In lowercase, apparently, because I didn't seem to care that Monday needed an uppercase. And then, obviously, the remaining 49 minutes you chuck in there. This is to be like as stupid accurate as you can, giving it in terms of even the day as well. But anyway, cool. All right, that's that one. Oh yeah, we are actually close to time, aren't we? Huh. Yeah, so I guess maybe just to reiterate, then you have all these answers available to you in the PDF. So I guess before this Zoom dies, maybe grab a copy of both of those. If you scroll all the way up, you'll have the 13H answers. If you scroll a little bit further down, you'll have where to locate this textbook stuff. And then from here on, the questions don't deviate too much from what we've already done. Like if I just sort of quick fire talk about a few things, like question 6 over here, you're given some stuff to work with. You're already given a base to work with. The initial value 100, so T0 is 100. Drops to 40 in 5 minutes. That's a point. Solve for K. It gets a bit repetitive at this stage now. Where things might get a little bit different, just as a final little tip here, for those who have not really studied limits just yet, there's this question about determining the limiting value of capital T as little t approaches infinity. Now, if you just sort of strip away any pretense of like math, as t approaches infinity, if t is a stand-in for time, then it basically means what happens as time shoots off to infinity. And so all you really have to do is consider, okay, I've got this t value that's attached to my exponential. The exponential has a base between 0 and 1, so it's actually going to decrease over time as time goes larger, as t gets larger. Now, this is CAS anyway, so you can just literally sub an infinity into this and you'll get your answer. But if you just sort of think about this in a tech-free way, as this gets larger, this gets smaller, right? Because your 0.98 as your t-value increases, that thing decays until what you're left with is the thing that's not attached to your exponential. You should probably already know this from your graphing of exponentials. This is an asymptote. So the limiting value of capital T is just going to be your 25, more specifically going to be 25 degrees Celsius, because that's what our question is talking about. And maybe as a final little thing, what does that value represent? The book calls it room temperature, which, you know, fair enough. It's a tub of ice cream taken out of the freezer. The final value that you reach is probably going to be room temperature. However you want to explain it is up to you. That's not really bulletproof as far as VCAR is concerned, so you're not going to get little questions like that. Or if you do, they'll accept a wide variety of answers, which would be, oh, this is just the final temperature that we reach. Or this will be the steady state temperature of the ice cream. You know, stuff like that. I think that's about it, really. That's the only weird thing that comes up. Maybe don't do these question 16, 17 ones. I didn't include them in the doc because I didn't think them relevant. This means you have to use some special shit on the CAS to make it work. Most schools don't care about this. Yeah, alright. I'll stick around for a little bit. Otherwise, that's about it for the lesson. So if there's any lingering questions, feel free to ask them. Otherwise, take care.